In this particular video, we're going to look at graphing radical functions, and we're going to do it without the use of a graphing utility. I will do another video showing you how to graph these in the calculator, but for right now, we're going to do these by hand so that we get a little bit better understanding of how these radical functions work. And we're going to be looking at cube roots and square roots. So let's look at our first example. We want to identify the domain and range of 1 through 4. So I'm just going to do a couple of these examples for you. I'm going to do number 1, and then I'm going to do number 3. So for number 1, we want to identify the domain and range of that particular radical function. So if we remember, domain are your x values. And that's another word for your input. That's what you're in input to the function, okay? So the domain is your x values. The range are your y values, which we also call your outputs. So you're going to basically take the domain values, you're going to plug those into the equation, plug those into the function, and the function is going to give you an output, which is your range. That's how a function works. So we're going to look at number 1, and let's look and try to figure out, without a calculator, what my domain would be. Now my domain encompasses all of the values that I could substitute into this equation successfully and still get a real output. Real meaning not not square root of a negative number, something where we actually get a real number output. Dealing with square roots, the one thing that we know is that we cannot have the square root of a negative number. We can, and we've discussed that, and that's I, which is an imaginary value, but we're not interested in I right now. We're interested in something concrete that we can actually put on these graphs. So let's look at this function. Knowing that I cannot get anything smaller than 0, because that's the smallest number, real number I can take the square root of. I can't get anything smaller than 0 under this radical sign. That means that my x value has to be greater than or equal to 2. The reason for that is any other value less than 2. Let's say I plugged in 1. What if I plugged in 1 for x and made that my input? 1 minus 2 is negative 1. I can't take the square root of negative 1. I can't get a real output. I can get an imaginary output, but we're not looking for imaginary outputs. We're looking for real outputs. So I plug in 1, doesn't work. 2 is the smallest value I can plug in for my domain and still get a real output. So that's my domain. So let's look at the range. D is your input. The range is your output. Well, if the smallest value I can get for the radical portion of this expression and this function is 0, that means the smallest y value I can get is 0 plus 5. So my range is going to be all y values greater than or equal to 5. Now, what exactly does this mean? If you had your graphing utility and you were able to graph, what you would notice is the behavior of this function. We're at 2 and 5. You would see that your function starts here and curves this direction. That's what a square root function or a radical function, if it's square root, looks like. And you'll notice there's nothing on this side of 2, and there's nothing below 5. If you were to graph this on your calculator and you tried to find an x value smaller than 2, your y value in your table would say error. If you tried to find a y value smaller than 5, the y value in your table would say, or the x value would say error. It won't even let you get there. So that's a good way for you to figure out what your domain and range are when you have access to a graphing utility. But knowing what each of these entails and knowing that you can't get anything smaller than a 0 under the radical sign, you know that the smallest the x can be is 2. Therefore, the smallest the y can be is 5. Okay? And this is kind of like HK. When we talk about HK form with quadratics and absolute value functions and cubics, and we've talked about HK. Well, you're in a similar situation here. This is your HK. This is going to be your starting point, 2, 5. So let's now go down here and let's look at this cubic function. Okay, so that's how you do the square roots. So let's look, cube root function. We did square root, and now we're going to do cube root. If you notice, there's a little index number there that's a 3. That tells you what the root is. Remember on the previous video, we talked about how the radicand is the expression under the radical sign, and the index is the indicated root. So we're looking for the cube root. So let's look for domain and range on this. Now, cube roots are a little bit different than square roots. We can take the cube root of a negative number. We cannot take the square root of a negative number. And here's an example. If I have -8 and I want to take the cube root of -8, that's asking me what number did I multiply by itself 3 times to get -8. And this is definitely possible because with an odd number of factors, that's -2 times -2, which gives you +4, times -2, which gives you -8. We do the positive case. Let's say I find the cube root of 8. It's 2 times 2 times 2. So these are both possible. So I can actually have anything I want, any real number I want under this radical sign when my index is 3, when it's a cube root. So my domain is x is all real numbers, because I can input anything I want for x in a cube root, because I can take the cube root of positives or negatives. It's not restricted like the square root. So let's look at the range. Well, if the range is an output of the input, which is the domain, if I can get all kinds of values for this, negative and positive, that means I'm probably going to get all kinds of values as an output. So y is also the set of all real numbers. Okay, now let's put this one on the graph. Let's see what this looks like. So if I were to actually do this, and I'm going to do this over here on the side, on this side, that means that whatever graph I have, there's going to be all real numbers. I'm going to have everything. It's eventually going to get to negative infinity, always all the way to positive infinity for both x and y. So let's first look at our HK point. Well, HK follows the same. Remember, H is the opposite of what's underneath. That's how we got 2, and K is the same. So our HK, or our starting point here, would be -1, -4. So I'm going to go to -1, -4. So that is either going to be our starting point or it's going to be our inflection point. And an inflection point is a point where the graph changes behavior or concavity. And we haven't really gotten into that, but for our purposes, it's just a place where the graph changes its behavior and starts going the other direction. So I have a point here. So that is the point -1, -4. So let's look at some points on either side of that now. Let's plug in some values. So I'm going to take this here. And we have perfect squares. We also have perfect cubes. The first perfect cube that we have is 1. So I'm going to plug in x equals 0. So if I plug in 0 here, I have the cube root of 0 plus 1 minus 4. Well, 0 plus 1 is 1. The cube root of 1 minus 4. The cube root of 1 is 1. So I've got 1 minus 4, which is negative 3. So that means that I have a point at 1, negative 3. Okay. Actually, sorry, apologize. 0, negative 3, because 0 is what we plugged in. 0, negative 3. So let's look at some other way to get a cube root. If I wanted to get negative 1 would also be a cube root. So how would we get negative 1 here? I'd plug in negative 2. So let's do another example, and I'll do the cube root of negative 2 plus 1 minus 4. That gives me the cube root of negative 1 minus 4. And the cube root of negative 1 is negative 1. So if I plug in negative 2, I get negative 5. And you can see what I'm doing is I'm just plotting the behavior of the graph. I'm just plotting the behavior of the graph. So you would keep going basically, and you would get something similar to this. It's not going to be absolutely exact, but we do have a y-intercept. In order to get an x-intercept, this would have to come out to 4, so we'd have to get 64, and that's way down, like 63. So what we're going to end up with is something very narrow on its side that kind of looks like this. And you can see there, that's your point where it changes behavior. That's your inflection point. So now that we've done that, let's move down to a couple of these graphs, and let's specifically focus on the graph. So let's look at number 5. Number 5, we have the square root of x plus 5. So again, and just so you see it, HK form is a times the square root of x minus h plus k. Okay, that is what we've been using as our model. So let's look at HK. What is my h? Well, it's going to be 0. So my h is going to be 0. And what's my k going to be? 5. So that's my inflection point. 0, 1, 2, 3, 4, 5. That's either going to be my inflection point or my starting point. Now, since this is a square root, it's going to be your starting point. Okay? A cube root, it will be your inflection point. So let's pick some values on either side of 0. Let's plug in 1. So if I plug in 1, I have the square root of 1 plus 5. The square root of, and this is for 1. The square root of 1 is 1. 1 plus 5 is 6. So I have a point at 1, 6. Okay? So let's plug in another point. Let's pick something else I can put under the radical sign that would give me a perfect square. So let's pick 4. So I'm going to plug in 4 for x. That would give me the square root of 4 plus 5. The square root of 4 is 2 plus 5 is 7. So my next point is going to be at 4, 7. Okay? And for our purposes, that's about all we're going to be able to fit on the graph that we have. But you can see the behavior of the graph. It starts increasing, and then it increases at a slower and slower rate. And that is what a square root function looks like, just like the one we did in number 1. We had our starting point from HK, and then we increased. So let's go ahead and go to the next page. And on the next page here, as soon as I find it, we have some cube roots. And the cube roots, you're going to graph them the same way. You're going to look for your HK. And remember, your HK form is y equals a, make sure you can see that, a times the cube root, that's a 3, x minus h plus k. Oops, I put 5, that's k. So hk is going to be, again, your inflection point. That's your point of inflection. So HK is going to be your inflection point. That is where the graph changes its behavior. And for certain types of graphs, concavity. And we haven't talked about concavity, so don't worry about that. So let's look at, while we're here, let's go ahead and let's look at number 12. Let's look at number 12. There you go. So let's look at the graph at number 12. Number 12 is a cube root. You can see the index is 3 over the radical. So let's do our HK first. Well, even though the K term is written here, I could, if I want, rearrange it to look like this. All I've done is move the 2. Now I'm in HK form. And if you remember my inflection point, H, well, there's nothing there. That's the same as x minus 0. So my x coordinate is 0 and my y coordinate is negative 2. So on the graph, that's my point of inflection, 0, negative 2. So let's find some points. We know the graph changes behaviors at this particular point, so let's find some points on either side. Well, we want to look for something that we can easily take the cube root of. And one of the things that we can easily take the cube root of is 8. So we're going to start with 8. I'm going to plug in 8 for x. So we'll make that our first point. I'll plug in 8. So if I plug in 8, I have the cube root of 8 minus 2. Well, the cube root of 8 is actually 2. So that gives me 2 minus 2, which is 0. So when x is 8, y is 0. So over at 8, we have a point right there. Okay? So let's go on the other end and let's go negative 8. So I want to find the cube root of negative 8. So negative 8 is going to be my point. So negative 8 minus square cube root of negative 8 minus 2. Cube root of negative 8 is negative 2. Negative 2 minus negative 2 is negative 4. So if I come over to negative 8, the point's at negative 4. But that really doesn't help me necessarily establish, it helps me establish how compressed the graph is or how stretched it is. But I really need one more point in between those so I can establish the shape. Well, there was one point that we could have used, and that is 1. Because in addition to 8 being a cube root, so is 1. 1 is a perfect cube. So I'm going to take this and I'm going to plug in 1. So the cube root of 1 minus 2, and the cube root of 1 is 1. So I have 1 minus 2, which is negative 1. So I have a point at 1, negative 1. On the other side, let's do the negative 1, because we can take the cube root of negative 1. The cube root of negative 1 is negative 1, and negative 1 minus 2 is negative 3. So negative 1, negative 3. Now I have enough points that I can establish the shape of my graph. So my graph is going to look something like this. Hits your inflection point and then changes behavior. And don't forget your arrows on the end. I don't always remember to write them myself, but we do know that we need to indicate that the graph keeps going. So that is how you graph basic cube roots and square root functions.